My name is Jesse Hoey, and I'm a professor in computer science at the University of Waterloo. Today I'm going to be a bit speculative about the limits of statistical machine learning, and so what I'll call socially sustainable machine learning, or machine learning that is able to handle whatever our society is going to throw at it, which is going to include the effects of climate change. So I'll start by talking about swans, which before the Europeans discovered Australia had been exclusively white. So if you ask somebody at the time, what color is the next swan that you're going to see, they'd say, well, white, because swans are white. But then when they got to Australia, they saw these new birds, and they had no way of interpreting what these things were. Okay. So the moral of the story is if you base your predictions on the past, then invariably you will be wrong. And a black swan will come along and disrupt your predictions. So I'll use the term black swan metaphorically to denote something that is unforeseeable and also catastrophic. So categorizing swans may not be all that catastrophic, but if you're predicting the state of the economy or a public policy, then the effects might be much more dire. So this comic from Nassim Taleb's excellent book, Anti-Fragile, shows this learned finance professor who's making a prediction of some value after some specific day. Unfortunately, this learned professor is a turkey, and he's predicting his own well-being. And so for the first 1,000 days of his life, he's been well-fed and watered, and everything's gone fine. And so if you asked him what was going to happen to him on the 1,001st day of his life, he'd say, well, I'm going to be fed and watered and housed, and everything's going to be fine. Maybe with a small range, might be a little colder or a little warmer. Unfortunately, the 1,001st day is Thanksgiving Day, which is the turkey's black swan, and the actual outcomes were very, very different than the range he had predicted. So this is not just a caricature. It happens again and again in history. We can look back to the 1700s in Prussia, where they thought, well, we'll increase the efficiency of our forests by making all the trees the same culture, the same species. And this took a little while. Things worked great at the start, but then eventually the forests were wiped out completely by a single invasive species of some kind, and this caused great economic hardship throughout the country. So this mistake is still being made today. We have the people near me in Waterloo who are trying to increase the efficiency of crickets. And so crickets are thought of as a food source. And so if you increase how efficiently you're growing these things, then you'll do well. So what they want to do is they want to track everything from environmental factors, cricket growth, and so on and so forth, and then use AI in order to optimize all these different factors. So they do acknowledge that they're going to need enough examples of sick crickets to get this to work properly. Okay? Unfortunately, they don't just need sick crickets. They need crickets that are sick with something that they've never even heard of before. They do acknowledge that working with automotive and aerospace components is going to be a lot simpler than tracking the health and well-being of living, breathing crickets, however. So we can ask ourselves, why would that be? And the answer is that the living, breathing crickets are a complex system. A complex system is one in which there are many interacting parts. They interact over a long distance, and there are path-based effects. So where the system goes next is based not only on where it is now, but where it came from, so where it got to where it is now. So this is the famous story of the butterfly flapping its wings and causing an earthquake in some distant part of the world. So we know that the complexity is going to emerge or give rise to black swans. So the black swans are somehow in this complexity, and they are unforeseeable just because we have no idea how these things are. It's very difficult to model how these different parts are going to interact to create these outcomes. So climate is a complex system, as I'm sure we're all aware. So we know it will generate black swans. So what will they be, and can your AI handle it? So actually, you don't want to ask the question, what will they be? Because we've just seen that it's impossible to know that. But we need to accept that it's impossible to know it and still ask the question, can your AI handle it? So I liken statistical machine learning to a beam search where you're shining a flashlight into a dark forest. And the dark forest is all the possible data sets that you might ever run into, including those that contain black swans. The beams you can use are narrow beams that brightly illuminate a small area, or wide beams that diffusely illuminate a large area. So your objective is you need a small enough beam to make sure you can see what you're looking at, but you need a big enough beam not to miss the black swan. Okay, so let's see how this works in practice. So in normal reinforcement learning, which is one common type of machine learning, which is fairly general, we try to learn a model, which is a function, from histories into actions. Okay, and the actions can be defined very generally, like investments or public policies or movements of a drone. And the functions are drawn from a class of functions or a class of models. In a model-based reinforcement learning approach, we also infer a distribution over some set of latent states. Okay, so we postulate some latent states and then infer a distribution over it. There's also model-free reinforcement learning, but I won't talk about that here. So most reinforcement learning uses a fixed class of models and a fixed latent space, so some deep neural network with some specific architecture. In Bayesian reinforcement learning, we accept the fact that we don't know what this model is, and we need to learn what it is and the class of models at the same time. So what kind of model are we looking for? So we infer a distribution over not only the states, but the functions themselves. So this amounts to Bayesian model comparison, is able to handle non-stationary environments, and it comes in many different guises. You might hear it termed meta-learning or learning to learn or active or sophisticated inference or even transfer learning. These are all the same kind of idea, but spun a slightly different way with different variations. The bottom line is now you can change flashlights. So you're given a big tub of flashlights with different beam widths and different directions, and you're allowed to pick different ones and try them out. To make this a bit more concrete, let's imagine we have some data, which is a set of input and target features, X and Y. And in this supervised learning problem, we're given a new input and we want the corresponding output, Y. So as Bayesians, we accept that we don't know the model, but we know that the model comes from some class of models. So to estimate the probability distribution over the target feature given the input and the data set, we sum over all of these models. To learn the model, we compute the probability distribution over the models given the data set, which involves also computing this normalizing factor, which includes the sum over models. This is termed the evidence or the partition function, or the negative of the logarithm of the free energy. So there's some things we can do here to get approximations to this sum, and some things you can do here as well. But the key is you're going to have to deal with this sum over models, and the question that we want to ask ourselves is how big does this class of models need to be? So let's look at a simple example of a reinforcement learner. So this water buffalo knows about two states of the world. There's grass and there's no grass. And it has certain expectations about those states of the world. So it expects to be able to eat in grass and not eat in no grass. And then it goes out into the world and it realizes the world, and the world fits its expectations. So it does get to eat in grass and doesn't get to eat in no grass. Okay? So that means that partition function is small, but it's big enough to handle what this water buffalo has to deal with, and the free energy therefore is maintained fairly small. Now let's introduce some new element into the water buffalo's world, which is this tiger, which is could be the water buffalo's black swan. Now the realization of the world is very different from the water buffalo's expectation, and there's lots of information there that the water buffalo can use in order to create structure and handle the problem. Okay? So it can detect that this free energy has grown, and then it can say to itself, well, I have to increase the set of models. So I have to increase that partition function in order to handle this. So it would learn then a state that describes tigers and another one that describes no tigers, and then it would have a four-state system that would allow it to react appropriately to the tiger being in the grass. Okay? So the fact that it had this distribution over models is a crucial element to this, because it allows it to make sure that one of these models is going to handle or have some kind of information about tigers. And this information could be carried over in a transfer learning style approach from different model spaces. So let's look at how big this sum should be. So the question is, how many models do we need to sum over, or how wide a beam do we need in order to make sure we don't miss the black swans? Mackay formulates it with this nice little picture of a tree with a box behind it, and asks the question, how many boxes are behind the tree? So you can think maybe there's one box behind the tree, that's hypothesis 1, or maybe there's 2 boxes behind the tree, that's hypothesis 2. There could be hypothesis 3, 4, and 5, and 100 as well, but let's just consider 1 and 2. 1 is a simpler hypothesis because there's only one way of putting a box behind the tree such that it fits this evidence. H2 is a more complicated hypothesis because there's many more ways of putting 2 boxes behind the tree such as they fit the evidence. So this box could be a bit smaller, and this one could be a bit bigger, and so on and so forth. Okay? So the fact that there's more configurations that are available here means there's more possible ways to construct this model so it fits the world. So that means it's less certain that the world fits the model as well. So if we look at this as the set of all data along this axis here, so that's like the dark forest, and this is the brightness of the beam, or how clearly it's going to illuminate the situation, then hypothesis 1 is going to make a very good prediction about a very small number of data sets. So there's really only one box, but it makes a really good estimate of where that box is going to be. H2, on the other hand, predicts more data sets, so it predicts all these different ways of putting 2 boxes under there, but each one it does so less well. Okay? Notice that this is only the likelihood function I'm talking about, so this has a built-in simplicity bias even if you're not a Bayesian, even if without including the prior function. All right, so this corresponds to the bias and variance trade-off in machine learning. And so again, the basic idea is you would like a low bias and low variance set of models. So this is a wide beam that's very, very bright. But we've just seen that these 2 things are complementary. You can't have them both at the same time. So what you need to do is ask yourself, how high a variance in my model fitting can I handle in order to maintain the kind of bias that I'll need to detect the black swans? So how do we implement this in practice? Well, we usually have a 2-level model. So we have some set of states describing the world, and then some set of models, parameter spaces describing the models, and some transform functions to go between them. And we can include time, we can include evidence, and possibly also other observations of the model space directly. My own research is to relate this parameter or model space to social, psychological, and sociological notions of group dynamics and values. What this implies, if you do this, is that this model space is actually an estimate of cultural structure, and the state space is an estimate of individual structure. And the objective of the agent is to try to trade these 2 things off. These back-channel observations then are revealed as emotional signals that people use in order to send elements of the structure to share them with each other. What this also means is that the group itself is somehow in control of the model space that each agent of the group is using. So there's a common fallacy in artificial intelligence that doesn't happen. This is a quote from the Connectionist mailing list just recently by a renowned artificial intelligence professor who says the brain, after all, is a physical system, and teaching and understanding is embodied in that physical system, not outside it. So understanding is just part of learning, nothing more. I disagree with this statement. I think that the groups in which an individual is embedded can provide this external understanding of a situation. And I believe this is done through emotional signaling. So understanding is simultaneously a group and an individual effort. The work that I'm doing in practice right now is in collaboration with my PhD student, Kyle Tilbury, and we are looking at multi-agent reinforcement learning problems. So these take things to another level and say now you have a whole bunch of agents trying to act together, and you apply reinforcement learning techniques to the same problem. The problem that he's looking at is called cleanup, and cleanup is a game in which there are apple trees that grow apples. These are the food for the agents, and there's a river that gets filled with garbage. And if the river gets too filled with garbage, which it does at a certain rate, then the apples don't grow. So the agents need to somehow divide the labor up between them and figure out who's going to pick apples and who's going to grow, who's going to clean the river. So Kyle's using the method of Jacques et al. That has a social influence factor in it, and he trains this for 100 million time steps, and you can see that the agents sort of figure out how to do it, and maybe this is tapering off, but maybe they'll get even better over time. Okay. This little negative glitch is because these agents also have a way of zapping each other, so they can incur a negative reward for themselves. Then what Kyle's doing is he's suddenly changing the rate at which the garbage accumulates in the river. And what we see happens to the average reward of this reinforcement learning system is it catastrophically collapses. Okay? And then not only that, but it seems to have a hard time recovering and starts learning even more slowly than it was doing before. So this is a fragile system. It is unable to handle the black swan. But what you can do is think about, what if these agents, as they were going up here, had managed to symbolically figure out the function that related the rate of garbage arrival with how many agents were doing the cleanup. If they had been able to estimate that function, then they would have been able to recover from this catastrophic loss much more quickly. So they would have been able to very quickly just change the parameter of the function and rebound very fast. I'll note that this change in rates is actually very small, and so it doesn't take much to offset this system the way that it is, and so therefore it's very fragile. So I'll thank my generous funders and leave my coordinates for any questions, and thank you very much for listening.